All right. Okay, cool. So this is systems project number one, the customizable shell. And we have one help session today, and we also have one Wednesday. So if you don't think I explained this well, you can always pop in Wednesday. And like I said, I'll be recording this, and we'll be uploading to the project page, so you guys can refer to it at any time. So in today's video, we're gonna look over the shell concepts, project overview and logistics, version control using Git, debugging, advice, and Q&A. And by the way, if you guys ever want to ask any questions, feel free to unmute yourself, drop it in the chat. I'll go over the answers at the end of each one of these topics. So yeah, just keep your questions prepared, put them in the chat for me. And we'll have a Q&A section at the end, like I said. So yeah, shell concepts. What is a shell? And I have this handy little GIF down at the bottom for you guys. But basically, a shell reads user input and it executes user requests. And there's a distinction here between a terminal and a shell that you guys may or may not know, and I'll cover it now. But basically, a terminal is the front end of a shell. So you see on the left side here, we have just a simple GNOME GUI terminal. And I put some examples. We have GNOME terminal, we have Terminator for Ubuntu, terminal.app, which is the Mac OS version. And down here, actually, the software version of a terminal comes from the basically the dumb hardware devices that they had like in the 70s, 60s, 80s, those years. So that's what they had beforehand. And if you have one of those, I don't know if I can help you, email tech staff or something, maybe they can get you back from the 80s. But basically, so that's the terminal, that's the front end, the GUI version. And then we have our shell. And a shell is simply an executable. It doesn't have a front end. And you type commands into it. And like you learned with exercise 1, it'll fork off different processes and execute stuff. So here we're running the ls command, and you can see all these different folders and files. And in this case, we actually have the environmental variable shell that we can echo and find the currently running shell. In my case, I'm using ZSH. So yeah, that's kind of the basics between a terminal and a shell. And this is kind of the behind the scenes version of it. So if you run a command in Unix, basically what happens is you have in your shell, it forks a child process. In this case, it would be the echo command, and then you pass it arguments, and this is an entirely different process. Nothing's happening in the shell process. It's simply forking a child, so nothing is happening there. So as I put in this infographic, we're waiting for the user input from the shell. It interprets a command, forks a process, and then, like I said, the parent and child go separate ways. The parent basically repeats the whole process of waiting for the user input while the child executes that one simple command. So that's kind of like the behind the scenes version of that. And here's some additional features for the shell. So what I explained before, this is a very simple forking process. And if that's all we had you do, it would be a very easy project. It would basically just be like exercise 1, but we're gonna have you do a bunch of additional features, and I'll kind of explain those down the road. But in a nutshell, we're gonna be doing foreground, background processes, built-in commands, IO piping, IO redirection, and signal handling. And I'll go over what each one of those things are. So as I said, we have foreground, background processes, and I love my animated GIFs, so I'm putting those in the PowerPoint as well. But basically, our foreground processes are basically what's controlling the terminal. So they have access to that, and you could type into standard input, and it'll go right into the process. As you see with the sleep 1000 command that I'm typing here, you click enter, and then it just waits. It's blocking until like the sleep command finishes, but we have control over the terminal here. Whereas on the right side, background processes do not have terminal access. And if you use a little ampersand operator in Bash, you could see that these processes are backgrounded, and you could still use your shell while these processes are still running. So that's kind of interesting. So you have those features baked into any normal shell, and you're going to be putting this into your own shell. And so, as I mentioned, there's built-in commands. These are commands that are defined within the program by you. And you don't need to fork or execute anything like that. So I have a list of built-in commands that you're going to need to implement into your shell. So we have the jobs command, and if you type this into your terminal right now, it'll tell you what jobs are running. And I encourage you to try this on your own, by the way. You could type any command you want, put the ampersand at the end, and when you type jobs, it'll come up with a list. There's kill, kills a process. You could send a specific signal to that. Stop sends a sig stop signal to a process, so that stops. Foreground sends a process to the foreground, background sends a process to the background. And again, we'll go more into depth with that a little bit later. But 2 additional built-ins and functionality extenders also required. So basically, this project is a little different than what I had to do when I took systems last semester. Our requirement was to make extensible plugins for our shell. In this case, we want you to do extra built-in commands. So you have to write 2 extra one of these. So those are the built-ins. And basically, as I mentioned, the built-ins behind the scene, you run the jobs command. It stays within the same shell environment, the same process ID as the shell. So you're not forking any additional processes. And as you can see here, we can see a process Vim has stopped and another process sleep, which is backgrounded. And the next thing that your shell has to implement is piping. And this is a very, very helpful tool that you can use in your shell. And again, if you did exercise 1, it's the same kind of principle here. So you type a command, for instance, ls, and then you can choose to pipe that into another process or another program, I'm sorry, in this case, grep, and then pipe that output into another process, wc. And so basically what's happening here is ls-l, that output will happen and will be sent to the grep command using pipes, as I'm sure you guys are familiar with exercise 1. And then that output from grep is finally sent to the word count wc command. So all of these are different processes, but you can just kind of imagine pipes in between these, which depend on each other's input and output. Yeah, so they'll wait on a previous process, final process outputs to terminal, and then the standard input and standard output for processes are joined to create the pipeline, as I mentioned earlier. So this whole command string is eventually going to come out with an output that looks somewhat like this. And this varies, obviously, depending on what directory you're in and what text files you have. But yeah, that's the basic idea. The next thing is IO redirection. Similar to piping, in fact, you're going to use similar dupe2 system calls as you did previously. And but what happens here is you are able to overwrite files or use files as input for your shell. So here are the different operators. We have the write caret symbol, which overwrites original file contents before writing out. We have the double characters, which is the same thing, but instead of overwriting, it appends to the end of the file. And then, of course, we have our left caret, which reads input from an existing file rather than standard input. And here's kind of an example of that. So we have our file output.txt, and then we have our echo, and simply forks a process and echoes welcome to system. Echo runs this argument, and the output of that goes into output.txt. So that's kind of simple, and you guys can try this by yourself. Sub out echo for maybe ls or something like that, any command you're familiar with, and you can see the output of that is written to a file. All right, so next we have IO redirection. And basically, as I mentioned before, that's where you're able to pipe in a specific file's contents as if it were standard input. So we're taking the file hello.txt, we're piping it into wc as standard input, and then it forks the process, and this is what comes out. So that's also pretty interesting, and you can do some pretty powerful things with that. Signal handling, as I mentioned before, shells can handle signals sent to them, and I'm pretty sure you guys got to this point in lecture talking about signals. But there's 3 primarily signals you guys need to worry about. We have a sigint, which is what happens when you type Control-C into your terminal, and you can try that out yourself. If you type a command like sleep 100, you type Control-C, it's simply gonna send the interrupt signal to that process, and by default, that'll just terminate the process. Then we have sig stop, and that simply sends the stop signal to a process and suspends it. That's the default behavior. And then sig child, That's the signal that's sent by the kernel to a process when one of its children dies. Um, and I'm going to explain this again later, but the only signal you guys really need to implement for this project is going to be sigchild. And again, I'll elaborate on that in a bit. So as I mentioned, handling sigints. So basically the shell and the single child process in the foreground are running. And when the user sends sigint, which is control C, to the terminal, it's sent to the foreground process group. And then this causes the group to terminate and the shell reacquires terminal control. And like I said, you guys might not need to worry about implementing this because basically, I think by default, the foreground process group gets any signal sent to the terminal. Same thing for sig stop. Shell and the single child process are running in the foreground. User sends the sig stop, which is control Z. And then that signal is sent to the foreground process group. And basically it's forced to stop and the shell reacquires terminal control. So that's the basis for that. And then sigchild, as I mentioned, the kernel sends a process to the parent process when one of its children dies. And you guys are expected to catch this signal, install the signal handler. So just make sure you guys do that. Okay, and now we have WIF macros, which stands for wait if. And basically what happens is when one of the wait system calls is called, it will return a PID and a status for a child process that changes state. And basically using these C macros, and there's a bunch of them down here, wait if exited, wait if signaled, wait if stopped, we could decode the status to discover what state a process changed to. And so basically, like I said, you pass in the status here, which is returned from the wait system call. And using these macros, you can make conditionals to figure out what you want to do. Okay, so as we mentioned, there's built-in commands that you all need to implement. And we have some ideas for you. Like I said, last semester, our project was a little different, so we had to do this in plugin form. But basically, the built-in commands for your shell, they should be, their implementation should be related somewhat to the shell. And what I mean by that is don't make a plugin or don't make a tool or a built-in that's simply what a normal program could do. Make it somewhat related to your shell. In our cases, like you might do a customizable prompt, so maybe your prompt is a little different. Glob expansion, and what that basically does is allow you to turn the star.c into a list of files. Setting, unsetting environmental variables, timing commands, all this different stuff. I'm not going to read over the whole list, but you guys get the idea. And as I mentioned, implement only functionality that is not already supported using Unix commands. And if you have an idea that's not on the list, please let us know and we'll approve it for you. So I'm going to just look through the chat real quick since we're on a new section. Can you elaborate on what not to do? What do you mean by something a normal program would do? Okay, that's a great question. Let me go back here. So let me give you an example. So a normal command might be something like maybe the time command or the dir command, the cd command. Those are not built-ins. And so basically, you want to be able to make a plugin that relates to the shell functionality. So in this case, like I said, customizable prompt that relates directly to the shell. That's something you can hard code into your shell, no problem. And executables won't really be able to have this functionality. They won't be able to say, okay, make my shell look like this. Glob expansion, same kind of principle. These are all things that your shell can implement, but not any arbitrary program written in C. Okay, so other questions. Do I need to understand how the linker works for this project? I don't think that's a requirement for this project, but I'll get back to you on that one. Will the recording be posted? Yes, it will be posted. We'll put it on the project page. Okay, next question. For implemented commands like jobs or kill, do we have to support all the different switches? Yes. So, well, actually, I think that depends on what the spec says. And like I said, the spec is different from last semester. I can get back to you on that one. I think the kill command is the way that we implement it is just one argument with the job ID, and that simply just sends the kill signal to the foreground process group. And then jobs, same principle. I don't think that one really requires any arguments. And you guys can use a box cush shell that he has. And I think in the spec, it tells you which directory to find that. And you guys can experiment around with that. But no, I don't think you need to support all the switches. Just make sure you follow the spec for all the built-ins. Okay. Oh, kind of elaborating on that, you do need to support arguments passed to like just regular commands. For instance, ls-la. I don't know if I was clear about that. All right, any final questions before I move on to this next section? Okay. I don't think we have anything, so I'm going to carry on. Okay, so basically, I'm going to go over some of the program requirements. So we have a couple of milestones for you guys to make things easier. We have our basic functionality. It's worth 50 points. And basically, in a nutshell, you're doing all the easy stuff. You're going to start foreground and background jobs. You're going to implement built-in commands like jobs, foreground, background, kill, and stop. And you're going to do signal handling. And if you budget your time wisely, this shouldn't take too long. The advanced functionality, of course, is the harder stuff. But with exercise 1, if you guys completed that, it's a lot of the same principles with I/O pipes. I/O redirection is something you guys aren't used to yet, but like you could simply open file descriptors using a system call, and like that should be pretty straightforward. And if you're unclear about anything, the TAs can help you, or you can check out the man pages. And then we also have running programs requiring exclusive terminal access, for instance, Vim. And this requirement basically ensures that your terminal state doesn't get messed up when you type a command like Vim, which takes control over the whole terminal. Dr. Bach included a lot of helpful functions for you to use to manage terminal state, and I highly encourage you guys use that. Extra built-ins, like I mentioned before, those are the built-in commands you want to implement. So like jobs, kill, foreground, background, but you need to make 2 more, as I mentioned. Version control, you are required to use version control for this project. If not, you will be docked 10 points. So make sure you guys know how to do that. And I think in this PowerPoint, we have a slide or a couple slides on version control. So I'll quickly go over some of the more useful commands. Lastly, documentation. This should be the easiest part. Always as you're coding, make sure you document well. So, you don't have to do it as extensively as you did maybe in, say, 3114 or 2114, but it's always nice to have a comment explaining what a function does, and just heavily comment your code in general. And this will be a huge lifesaver to us TAs if we have to help you out on your project. So before you start coding, take time to read over and comment over the starter code. And the starter code it may look daunting, but I think it's a cush.c file. That's the main entry point file. It is already heavily commented, and you should be able to figure out what it's doing. And in fact, we were nice, and we have a lot of the functionality already done. So we have like a abstract syntax parser. So you don't need to parse the whole commands. You could just rely on the code that we have already. And if you compile it, you can kind of see what I mean by that. If you compile like the base shell that we give you, and you can see how the parsing is done. So you don't need to worry about any command parsing, which is kind of nice. Read the provided lecture material in chapter 8 in the textbook. Highly encourage you guys to do that. And if you did exercise 1, you might have a lot of that bulk knowledge already, as I mentioned here. But basically, yeah, this project is going to have the fork exec model, and we have all these different piping operations. And as I mentioned previously, check out Dr. Bach's example shell. It's in this directory. And you can definitely strace that if you want to figure out what it's doing. You could definitely run it and try to put in your own commands and see what happens. But yeah, the Bach shell is there to help you out. And as I mentioned, base code already has a syntax parser, so you don't need to worry about making any of the commands to parse the commands. Okay, so I'm going to talk a little bit about the data structures that are in your project. So if you guys have looked out on the spec already or the code, you'll notice that there's a few data structures that are important. The top level one is the AST command line. And that's what the parser, as I mentioned, it's included a parser. That's what the parser spits out when it registers a command. So in this case, let's look at this command: sleep 10 ampersand semicolon echo high, and then pipe operator, and then reverse. So that's the AST command line. That's what this is taking care of. And then below that, you have the AST pipeline. And a pipeline is simply just a list of commands that all communicate with each other. And then below that, for each, we have an AST command, and the AST pipeline is simply a list of that. So in this example, again, this gets split up to a pipeline. There's one command here, sleep 10, and we know this one's going to be backgrounded because it has an ampersand. And then this is our AST command. And then for the right side, and by the way, these are two completely separate pipelines, so they won't be communicating with each other. And so the right side is echo high, and then we pipe that into the reversing commands. And then these split into two of their own commands, AST commands. This one's echo high and this one's reverse. And like I mentioned before, you're expected to create pipes in between these processes so that the output of one process and the input of another process are connected. So those are the data structures. And then we have the list data structure. So we're given a linked list data structure class, and that is implemented in the list.c file. And you can also look at the list.h file for the API. And basically, I'm pretty sure every project uses the list.h class, so just make sure that you guys are utilizing it as much as you can. And for every subsequent project, if it's not included, you're more than welcome to include it. It's your code. And I would look through the list.c before using it. It could get pretty complicated, but I'll try my best to clear some things up. So in a nutshell, if you guys remember from like 2114, 3114, so we have our standard linked list on the right side, and basically here we have a list node, and we're able to link it to more subsequent list nodes. And so that's your regular linked list, and you have, of course, your data, and this is a generic, and so you can set that to be whatever you want. On your left side is the C version of the linked list that we have you implement, and we have a pointer to the left list element and a pointer to the right list element, and basically any struct that you want to be list iterable, you want to include this list element in there. And the nice thing is you can use this nice little list entry macro to convert, as you're iterating through, you can convert a list element into the struct that you want to. In this case, we're converting this list element into the AST command struct. So that'll be very useful when you parse the pipeline. And here's an example of an element in a list. So here's the AST pipeline struct. And as I mentioned, we want to put the list element here, and this makes it into an iterable data structure. So as I said, adding list element to a structure allows the structure to be added to a list. And here's some list pitfalls. So don't use the same list element for multiple lists. I actually had to help a few people out with this problem already, and there was a question on Piazza about this. But basically what happens here, if you have two lists that contain a single element, you could run into a bunch of problems. And one of the problems is a use after free. So imagine you free one of the lists and all the data is in the list. The other list has a now free element. So that's going to cause a bunch of invalid writes. And if you run Valgrind, you can quickly notice that. And we're going to show you a better way to do this. Also, don't edit an element while iterating. So if you start trying to remove elements as you're iterating through a linked list, you're going to have a bad time. And there's a better way to go about doing this. So here's an example of list remove. And you can see this in the AST pipeline free function. But basically, what's going on here is you use a list begin function on a specific list of commands in the pipeline, or for that matter, any list. And you keep iterating through until it reaches the end. But as you're iterating, you have the option of removing that list element easily. So that's what this is doing. And this is the safer way to go about doing that. So I highly recommend looking into this. Oh, and like I said, remember to remove a pipeline from the commands list before adding it to the jobs list. And that's what I was talking about before. If you have two elements that are exactly the same in memory and they're added, I'm sorry, if you have one element in memory and they're added to two different lists and you free one by accident, you're gonna have a bad time. In this case, make sure you always remove commands from the pipeline before adding it to the jobs list. And that will save you so much time debugging. Okay, I think we're getting close to the end of the implementation, but basically, here's some utility functions that we strongly recommend you use. So signal support, and we have some classes for you guys to look at for that. And these files are heavily documented. So feel free to look through the source code and look at these. You have signal block, you have signal unblock, and set handler. As I mentioned before, the SIGGILE handler is definitely something you should handle. So make sure you pass a reference to that function. And of course, you have the terminal state management. As I mentioned before, the foreground process group is going to want to control the terminal. And any background processes are not going to have access to it. So a background process won't be able to write to standard output, and it won't have access to standard input. But you can use these functions to give a terminal, and we give these to you. You can use these functions to give a terminal to any process group of your choosing, which is kind of nifty. When it comes to testing a submission, of course, please submit code that compiles. And if it doesn't, then I think that's a 0. But also test the driver before submitting. Don't just run the tests individually. And lastly, when grading, tests will be run 3 to 5 times. And if you crash a single time, it's considered failing. So make sure you pass all the tests in a milestone before you move on to the next one. But by any means, if you want to get pipes knocked out, feel free to work on some of the advanced functionality as you're working on the basic if you think you're up for that. Okay, so we give you a test driver, so you don't need to submit to the auto grader to see if you're doing things right. But basically, you can run the script locally, and it'll go through the basic and advanced tests. And so you guys can simply see if your shell is working without uploading. And there's different options you can pass to it. So like you could pass -B to just do the basic tests. And I mentioned what those were before. -A for the advanced tests, IO piping, IO redirection, exclusive terminal access, and -H, of course, lists the help for that. And then you need to write tests for your additional built-ins. So what you want to do here is you want to create .tst files in the test directory and create a directory that'll store your test scripts. And I've kind of put an example in here for you. So this is kind of the format of what you're looking for. You want to write the name for your tests, followed by the word tests. And then of course you want to attribute a points value to that. So how many points this test is worth, followed by like a category down here and down here. And this is what one of the milestone tests looks like. So you can kind of copy this format. Like I said, this is the point value, and these are the testing scripts that you're going to write. Okay, so make sure that your custom.tst file is of type ASCII text. So just make sure it's all ASCII encoded, not Unicode. And if you type the file command like this, it should tell you if it's encoded in ASCII text. So that shouldn't be a problem. And again, if it includes Windows terminators, like the /r/n, trim those off. There's a helpful Unix command line utility to help you with that. But if you do all your development on a Unix machine, you shouldn't run into this problem anyway. So I wouldn't worry about this too much if you're developing on Unix. Okay, as I mentioned, there's a design document you need to submit. So basically, you're going to have a readme.txt describing your implementation. And we're only going to credit you for functionality for which the tests cases and the documentation exists. We want to make sure that you guys fully understand what's going on with your shell. So we really do need this filled out correctly. Okay, so before I move on to the next section, I'm just going to look through the comments. Okay, so Peter said, by syntax parser, you mean the handling of the RVs, right? So, I mean, I guess so. Basically, the syntax parsing in this case would be parsing the whole command string. And we'll go back again real quick so I can show you. Yeah, so it's basically taking control of splitting this whole command string into different pipelines and commands. So that's all that the syntax parser is doing. So you don't need to worry about like creating any of these. These are already created for you, and you can access them through the AST command line. And Peter, does that answer your question? Okay, great. And then I got a private question. For list.c, could you explain the list rend method? It's identical to the list head method, so I'm confused if there's a mistake or not. So that's something I'd have to get back to you on. I've actually never used the list _ rend method. But is it commented in the list.h file? I'd have to double check that, but that's certainly something I can get back to you on. What does pexpect directory in the provided code base do? So let's actually, while I have you guys here, why don't we look through the code base so I can see, so I can kind of understand what it is. I don't think it's something you need to worry about, but let me just double check. Ooh, let me log in here. Okay, I think a lot of these files are to help with the testing. I don't think you really need to look through these files, but again, I could be wrong about that. The spec changed a bit from last semester, but I don't think you need to worry about that. I could be wrong though. All right, I think that's all the questions for now. Any last questions before I move on to the next section? And is my screen still sharing? Do you guys still see my screen? Okay, great. All right, so let's talk about version control. And before I really go into this, let me just share with you a story, a tragic incident that happened when I took systems last semester. I was working on exercise 1, the same one you guys did. And I was completely done. I had my answers.txt, I had my my source file, but I wasn't using version control. And basically what happened was when I was ready to tar my file, I switched up the arguments for the tar commands. And I essentially overwrote my solution for dpipe. And I was really mad about that. You know, dpipe took a little while for me to wrap my head around, but you know, I got it done. I was so happy, and then boom, I overwrote my code. And then I didn't use Git, so I couldn't restore my code at all. And from then on, I've been using Git as version control for all my exercises. And I encourage all of you guys to do the same for every exercise, for every project. In fact, with the projects, we require it. So make sure you guys are using version control. And there's a bunch of other upsides too, other than, oh, I lost my code, what do I do? It organizes it. So like you could simply view it in GitLab or another provider, and you could quickly see all your code in one place. Keeps track of your features. And I didn't write this slide, but what I assume he meant by this was like there's issue tracking in GitHub. You could file issues, you could assign issues to other people, and that's in GitLab as well. In fact, I use that for all my projects as well. My partner and I used issues, and we assigned each other issues. So if you guys want a way to split up workload, this would be pretty useful for you guys. And then it allows for collaborators. This is a big thing, especially this semester where you guys can't really see each other in person. But basically, Git allows you guys to collaborate remotely. So if there's a bug you're stuck on, Git push, have your partner pull it. You guys can work on the same code base. And like I said, backups whenever something goes wrong. I will never forget that. I will always use version control from now on. So next we have basic Git commands. And there's a bunch of different commands that you can use. Git is very big, but there's some very basic ones that you need to know. Git add adds a specific file to the Git tracker. And then git commit commits your changes to the Git tracker. And then once you're done, you can upload it remotely using git push. And always pull before you push because you wanna make sure you don't run into like merge conflicts and all that jazz. It's a very bad time. So make sure you keep this in mind. Here's some more basic Git commands. Git pull, that basically pulls from the remote Git repository. Git status tells you the status of all the version control stuff. And if you guys haven't set up Git access already, highly encourage you guys do that. But basically, you'll need to make an SSH key. And this is separate from the one you guys have configured on our login, if you guys have done that. But you make an SSH key, and then you copy the public key and you upload it to your cs.vt.edu keys here. And if you guys have any trouble with that, us TAs would be happy to help you set that up. Just let one of us know, and we'd be happy to have that set up for you. And then you can verify Git access to make sure this is all working. And you can do that simply by SSHing into Git. And if it works, it's going to say, welcome to GitLab, and then your PID. And then it'll close the connection. And so if I didn't go into that enough, there's a couple links down here: generate a key, use an existing key. And we're going to upload the slides, so you guys will be able to click on these links later. Okay, so here's the stuff more pertinent to this project. But basically, one of you guys, if you're in partners, will fork the base repository. So one of you will fork this in their GitLab, and they'll invite their partners to contribute to it. And you can do that under settings to members to add people. And then you got to make them maintainers too for them to have edit access. So make sure you do all of that. And then both members can clone the forked repository on their machine. And this is the part where you need your SSH key on your local machine before you clone any Git repos. So that's pretty important. Make sure you guys put the public-private key there. The most important thing of all, though, and this is very, very serious, so make sure you guys write this down. But when you fork a repository, you must set it to private. Otherwise, any code you do contribute will be viewable by anyone else inside of the VT GitLab. You don't want that because that could have serious honor code repercussions. So make sure you absolutely do this. And I'm sure we'll keep hammering it into your heads, but just make sure you do this. I think people have been honor coded from this before. All right, okay, I actually do see some questions in chat, so let me look through these real quick. I did the same thing for my CS3214 code assignment. Yep, happens to the best of us. And then Evan asked, you can push and pull directly from or to our login, right? So it won't necessarily be on our login, but basically VT has their own GitLab server, and you could push and pull from that. But yeah, I actually, maybe I'm understanding your question better now. But yes, you can configure your SSH keys, your GitLab keys on our login if you want to do all your code editing on our login. And the same goes for if you want to build and run your projects locally too. So both of those options are certainly avenues you can pursue. And Evan, did I answer your question there? Okay, great. Philip asked, is it required if that we use GitLab? Can we use GitHub if we make sure it's private? I think you're required to use GitLab just so that the TAs and VT tech staff can look at your projects. So I think you have to use GitLab. Although I could be wrong. That's also something I'd have to follow up on. I can ask Bach. Okay, William says he has his own GitLab server. The machine it was on crashed, and I thought I lost everything. Oh, that's a bummer. Okay, so I got a private DM asking, when trying to fork the repository, can we use VS Code for this, or do we have to do it on our local terminal? I assume you're asking about whether or not you can use VS Code to fork a GitHub repo, and I think you can. I think there's an exception to do that, but I would, if I were you, I'd simply use your terminal to clone the GitLab repository. Just makes it easier, and if you know all the Git commands, it just simplifies your life so much. So I highly recommend you guys do that. Will non-majors have any extra steps to gain access to CS Git? Actually, that's a good question. So I too was a CPE major once upon a time, and I was transitioning from CP to CS. So I was a CPE major, and I think I got force-added into problem solving. And I think if you're registered for a CS class, you automatically gain access to the CS Git. Oh, Benjamin said no, though. Maybe they changed something. If you don't have access, I highly recommend you email CS tech staff. And you can search their email. But I would try it out first. And if you have any problems, email tech staff. They could probably give you access. Peter said, I asked about that question on Piazza, and Box response made it sound like GitLab was required. Yep. Yeah. Like I said before, I think CS faculty and staff have access to the GitLab repos. So we just want to make sure you have your code there. And if we don't see it there, I think we'll dock the points for version control. So make sure you guys do use GitLab. And then Ben says non-majors should have access automatically. Yeah, so I guess I was right. And Peter said, per the requirements, use GitLab as, yep. Okay, any other questions for me before I move on? All right, I'll take that as a no. And like I said, I'll reserve a final Q&A section for the end, just in case you guys have any lingering questions. So this section is about the GNU project debugger. And this is something that I highly encourage all of you to learn because this has helped me so much in computer systems and finding and isolating bugs. And in fact, this has helped me in the workplace as well. So last summer and a couple of summers ago, I was working at this one company, a defense contractor for the federal government, and we were doing vulnerability research. We actually used GDB quite extensively to pen test code and attempt to debug vulnerable code. GDB is widely used everywhere. It's an industry standard. In systems, if you guys know this, you'll be rock stars, trust me. So make sure you guys know GDB. I'm going to give you a quick crash course on this, but basically you can invoke GDB with a program and arguments. So you see this command here. This executes a program called program and passes in arg1, arg2. And this is, in my opinion, better. Simply run the GDB command with the program, and then you can run it like this, run arg1, arg2. And I think there's also another command called set args that you can use instead of this. So whatever your preference is. And you could certainly look up a GDB guide online. There's a ton of useful commands to know. Here's some more. So here's how to set a breakpoint. You can either do a function name or a line number, or in fact, if you don't have the debugging symbols enabled, you could set a breakpoint on the function address, but I wouldn't worry about that. That's if you don't have debugging symbols. You can also set a conditional breakpoint, and you want to do this if you want the breakpoint only to execute if you meet a specific condition. For instance, what if we wanted to check the variable I in a for loop is like 57 or some arbitrary value? If we set this, the breakpoint, the program will break right when that condition is met. So that's really useful for certain things. Also, we can ignore a breakpoint X number of times. Again, this is pretty useful for when you're doing looping or other stuff. I'll be honest, I've never used this before, the ignore breakpoint, but I'll file it into my toolbox. I might need to use that in the future. And then of course you have info B, which shows the number of times a breakpoint was hit. So those are the basic GDB commands that you should all know. And if you know those commands, you'll be pretty successful. And you also have backtrace, which shows a function backtrace. And if you're inside of a function, you could see basically your call frame. So you can see the current function you're in and all the previous functions that it took to get to that point. And if you type frame and a specific number, you can select a specific function to inspect inside of GDB. So keep those in mind as you're debugging. For this project, these commands are pretty useful. Set, follow, fork mode, and then a specific mode. And I think this mode can be parent or child. This is really good for debugging processes that have children, because it can get pretty crazy pretty quickly. So yeah, that's set, follow, fork mode, and then set detach on. Okay, so after a fork, specify whether to freeze the child or allow it to run. And enabling this will make it difficult to find a race condition. I highly encourage you guys to use GDB while debugging this project. But like I said, it can get a little intimidating when your parent process forks a child, especially with all the like the dupe2 calls and the everything else. So just make sure you can kind of understand like how to run these commands. Okay, and layout source. So this GDB commands will allow you to look at the source code as you're running a program. Again, this only works if you have the debugging symbols enabled in your binary. But this makes it so much easier to look at your source code as you're debugging in GDB. I don't know if any of you guys have ever attempted to use GDB before, but you don't see the source code of your program as you're debugging it. You have to explicitly enable this in order to see the source. Any passing remarks or thoughts or questions before I move on to the advice section? Peter asks, astonished that GDB TTUI does the same thing here, same thing as layout source, right? Yeah, I'm pretty sure TTUI is the window management that GDB uses. Unfortunately, I'm not terribly familiar with it, but if I understand your question right, I think yes. Oh, wait, he elaborated. GDB TTUI does the same thing as layout source, right? Yeah, I'm pretty sure it does. But I could be wrong about that. Like I said, I don't know too much about TTUI. But that's certainly something you don't really need to know for this project. Like I said, layout source is fine. If you know how to use TTUI, you can certainly use those commands as well. So here's some advice. How can I fail systems? A very interesting question. So there's a bunch of ways you guys can fail systems. Number one, not utilizing class resources. Us TAs are here for you. Dr. Bach is here for you. By the way, Dr. Bach is one of the best lecturers I've ever had. And he is one of the most responsive professors too. And you ask a question, he responds usually within 30 minutes. He's such a great guy. And us TAs, we're happy to help too. We have TA hours across the clock every single weekday. I think there's some TA hours on Saturday too. So feel free by any means to come visit the TA office hours. Don't mismanage your time. It's another pitfall of systems. I see a lot of you start the exercises early, which is fantastic. Keep that up. One of the ways you can fail is simply not managing your time right, starting a project 3 days before it's due. And if you do that, you're just gonna have a bad time. We release the projects usually 2 to 3 weeks before the deadline. So that should be ample time to look through everything and make sure you do it right. So get a head start early. In fact, if I were you, I'd start this week and try to get the basic functionality done on the shell. At the very latest, maybe at the end of the week, get started. Not understanding your tools. So I highly encourage you guys to familiarize yourself with GDB, number one. Number two, Valgrind. One of the most important tools you guys can use for this class. I've used it countless times last semester. to debug like my thread pool project, my shell project, and find like a bunch of invalid memory operations. And Valgrind, honestly, in my experience, is the best way to find bugs. If you use it, like, and a bug is somewhere in your code, maybe 5 times out of 10, it'll tell you, oh, that's an invalid write. It'll give you the line number, and then you can instantly go back to that code and figure out what the problem is and patch it. Valgrind, super useful. GDB, super useful. Definitely keep those in your toolbox. Fail to get along with your partner. So if you guys have any issues with your partner, I think you can switch between projects. So just keep that in mind. I don't think you can switch in the middle of a project. I could be wrong about that. That's also something Dr. Bach would have to answer. Not break down the problem. So before I start any C project, I like to diagram everything. In fact, not just any C project, every project I do in coding, whether that be Java, Python, C, Rust, what have you. So what I usually do is I take my iPad out, or maybe a pen and paper, and I just simply diagram everything out. So like maybe I'll write, oh, this cush.c class, that's the entry point. That's where my program's gonna load. Then, oh, I'll have another class, or sorry, when I say class, I mean file. But another file that handles the like the command parsing, another file that handles the built-in commands. So just make sure you write all that out. Abstract your design. It just makes it so much easier further down the line, as opposed to like putting everything into one file and trying to solve that. Not understand the concepts. Again, another pitfall. For this project, I would highly encourage you to revisit the lecture slides that Bach has about piping, forking, exec, all that different stuff. So make sure you revisit those. Check out the man pages. And if you don't know what I mean by that, let me show you real quick. So in a terminal window, if I'm in Redbud, I can simply type man and then pipe. And that shows me one man page for pipe. And if I go to the second page, this gives me the C command, or the C function, which creates a pipe. And you guys can certainly look through this. These are very extensive, and they can help you a lot if you just look through that. So we have a pipe call, you pass it in an array of 2 file descriptors, and it'll populate that array. So man pages, very helpful. Highly encourage you guys use them. So yeah, that's all I have on the concepts. So here is another slide on advice. Start early. Like I keep hammering into your heads. Start early. Can't stress this enough. Start right now for this project. Start, maybe the week within any spec comes out. Create a roadmap, as I said, before starting projects. Utilize TAs. Always come, when you visit a TA, always come with questions prepared and try to solve the problem first. And if you can't solve the problem, then the TAs can help you. Be organized and have clean code. A lot of people have asked me for help, and a lot of them have really good clean code, which is really good. And the cleaner it is, the faster we can help you. So make sure your code is formatted, make sure it's clean, so that we can quickly go through, and heavily commented. This is something Dr. Bach posted on Piazza, but also something I really want to reiterate. Run Valgrind before consulting us. Like I said, Valgrind is one of the most helpful tools I've ever used in systems. In fact, in 2506 and 2505 as well. It can really quickly isolate problems. And chances are, if you come sit down with me in a TA meeting, I'm going to start doing this, by the way. I'm going to start having you guys show a clean Valgrind output, just like Mr. Bach, or Dr. Bach. So make sure you guys have clean Valgrind runs before consulting us. And if you guys have any issues with making those runs clean, we can certainly help you out with that too. I'm not saying like don't come to the TAs if you can't get a clean Valgrind run. I'm saying try your best, and if you can't figure it out, just talk to us. We'll help you. We're on Discord, Zoom, and Piazza, as most of you already know. So be sure to fully utilize those resources. Also, understand the exercises. X1, you guys just finished that. Got it submitted. Hopefully most of you understand what's going on there with the piping and the dupe2 calls and exec v and the fork. So just make sure you fully understand that exercise before working on this project. Otherwise, you might have a bad time. So just go through, understand what's happening. Run the S traces again if you have any questions, or run the S trace, like I said, on Dr. Bach's shell. As I keep mentioning, use Valgrind. We'll skip over that again. Become an expert at the debugger. Probably the best piece of advice I could give for systems. Just using GDB, figuring that out, and just being good at it. And you just certainly don't have to use GDB if you don't want to. There are many other debuggers out there that you could try. And I think VS Code even has like a GUI debugger, but I do highly encourage you to at least familiarize yourself with GDB, because in my opinion, that's the best debugger out there and the most versatile, and it could do a lot of interesting things. Find out what works best for communicating with your partner, whether that be over iMessage, Facebook, Discord, Zoom, what have you. In person, if you guys can do that safely. Doesn't matter to us as long as you guys are working efficiently with your partner. Okay, here's the ending slide. But basically, I ripped most of these slides from Spencer Kiefer, who was a TA over the summer, I believe. I just added my own addendums and my own examples. But most of this stuff, when this project was a different spec, was taken from Ken McDonough, Connor Shug, Joe Deanna, like all those guys. So yeah, that's pretty much it. Any questions? Oh, I see some already. Lol, he responded to something on Discord as he said that. Yep. Can you go back to back one slide? Okay, I thought you said back to slide one, and I was like, should I just start over? This slide? Or the one before that one? Okay, he's good. Any other final questions, and then I'll wrap up here. And so I have TA office hours tomorrow from I think 8 to 10. So feel free to join those. Right now, Jonathan has office hours from 7:30 to 9:30, I think. Can't remember exactly when, but like I said, we have TA office hours throughout the whole week. Okay, so I just got asked a question. Could you explain how we go about implementing a built-in command? I'm not sure where to start. All right, that's a good question. So let's go back to the slide where we talk about like basically the AST command line stuff. And actually, you know what? I think even better suited would be to go through the shell source code right here. So kush.c, and this is the source code that that we're giving you. So if we scroll down, like this is all the starting code that we give you. It's very heavily commented. Bach loves heavily commenting and stuff, which is really good practice. But basically, for the built-ins, you can simply implement them here if you want to, or you could call a function and abstract that to another file if you want to. So in my case, what I did for this project was I made a simple function called, first of all, I checked if any of the commands that were being passed through was a built-in command, and if it was, I would pass that to a function that handles the built-in commands. And if it wasn't, I would simply run through my shell logic, everything that doesn't have to do with built-ins. For example, forking, piping, exec.ve. So the built-in shouldn't be that bad. It's just a matter of string comparing the different AST commands. And if it hits one of the built-in commands like jobs, foreground, background, at that point, that's where you want to implement your built-in. Let's look at more questions. And did I answer your question for that one? That was a private message. Oh, okay. Bob, I'll get to your message in a sec. Let me answer Benjamin's question. Can you walk us through the Git repo so we know what's in there? Yep. Okay, so this is the source. Well, actually, let me go back one level. This is the px spec that another person was asking about. And like I said, I don't think you need to do any edits in there. I think all the edits are going to be in the tests directory. So I wouldn't worry about this. I think this is just to help us with the testing. But the source, so the test directory is all your test stuff. So you have your advanced, basic, and the milestone tests. And if you look through those, you can kind of see like how it's formatted. And I'm not going to spend too much time on that. That's stuff you can kind of learn from the spec. But here's the source directory. This is the good stuff. So we have our cush.c file. Of course, this is the entry point. And if you search the main function, oops, I accidentally opened something. But if you search the main function, this is the whole entry point, and so you can start writing your code like line 295 or wherever you see fit. And so this has a bunch of useful functions for you guys. And then of course you have your header files for this, and that'll just go into the API. Your list.c and list.h file, you need those for the list implementation. And you don't really have to use the list.c and list.h files if you don't want to. I really would. Like I highly recommend using these for some of your stuff. For instance, the jobs list. I would highly recommend using this and familiarizing yourself with this. Okay, so then the AST and the shell AST.c and shell AST.h file. AST stands for abstract syntax tree. I think somebody actually solved that in the chat. But this is all the parsing done for the command line stuff. You don't need to really look at these files. These are just there to parse the command line. And if you guys are in comparative languages, you'll learn more about this stuff. And then the grammar, also stuff you don't really need to look at. Signal support, these are just to help you with the signal handling. Term state management helps you with the terminal access. And then these are just like final utilities that you can use. And that's basically it for the source files. And you can certainly add your own source files. You can add stuff to the make file. Another thing I forgot to mention, whenever you add your own C file, you have to include it as an object in the make file. So just like it's written here. Okay, so I think I've kind of gone through the Git repo. Let's see if there's more questions. Something overlooking the code. I'm curious what we have to take into account with the static data structures with forked processes. Do we have to worry if we add something from the list at the same time as another No, that's not something you really need to worry about too much. So basically, when you're forking a process, you're not doing much besides running duplicate on the file descriptor, dup2, and your parent process is going to control mainly all of that stuff. So you don't really need to worry about the like accessing list elements or race conditions due to your child processes. That's a great question though, because right after you do dup2 and you fork and all that stuff, you're going to be running execve, and then the process instantly becomes another program. So you won't really need to worry about the race conditions there. He asked another question. Do we have to worry if we add something from the list at the same time of another process? And yeah, okay, so same principle there. Your child processes are not going to have to worry about the lists or any of that stuff. All right. Oh, another question. So other than the cush.c, the other files are just there to support base functionality. We are provided that as the base API, but we don't add onto those and are mainly going to be. Yeah, I suppose so. But yeah, so your cush.c is the main file you're going to be making edits on. The other files are there to help you. And like I said, highly recommend you add your own C source files to abstract the solution a little more. But yeah, did that answer your question, Joseph? Okay, great. Any final questions before I close the session? I'll just give it another few minutes just in case we have any lingering questions. But if that's it, you guys are free to log off. And like I said, I'm gonna go ahead and post these the whole recording onto the page, so you guys can check that out later. I'm assuming GitLab Git instructions are on the site. That's a good question. I'm actually not sure about that. I think they briefly mentioned setting up Git in the spec, and it's probably somewhere on the CS3214 site. But if it's not, there are countless tutorials out there. I would highly encourage you to Google how to set up Git SSH authentication, and it'll walk you through generating the public-private key pair on our login. And once you do that, you copy the public key from our login, paste that into the GitLab settings. And then once you have all that submitted, you should be able to communicate freely from our login to the GitLab server. But I'm not sure if the instructions are explicitly listed on there. And like I said, we'd be happy to help you out. Just come to one of our office hours. We can get that squared away for you.
Sorry, I have one more question with the kind of the same question on Valgrind.
Mm-hmm.
I haven't used that before, so I'm guessing there's instructions on the site, or this is another one of those like install it and Google.
So I think in previous semesters, like 2505, 2506, I think we had instructions for that. I kind of self-taught myself Valgrind because I didn't take 2505, but it's pretty simple to use. In fact, I can demonstrate it right now if you would like.
Okay. Yeah, I didn't take it either. I was CPE. So.
Yeah, same. I was in the same boat as you. But why don't we go to like one of my exercises? And if we run like Valgrind, and then like, did I compile it? I don't know if I compiled it. Oh, I did. strace new deep pipe. Wait, no, that's not it. You know what? I'll just compile it again. There we go. So you just run Valgrind, and then your file name. In this case, it would be Cush, C-U-S-H. And then it should just come out with a whole log. So you can see here at the top, like there might be uninitialized bytes in my solution. But other than that, like you should expect a clean log. And you can run this for any command and any compiled program. You also have the flag for Valgrind, leak check full, I think it is. So if you run that, it'll, oops, I messed up again. If you run that, it'll have the whole leak check. Oh, maybe I got that wrong. It's something like that. But if you check the man pages for Valgrind, it'll have a whole list of options that you can use. So certainly check into that. But I would say for now, just stick with the base Valgrind command.
Okay, sweet. Thank you.
No problem. All right. Any other questions? Speak now or forever hold your peace. All right. If that's it, I'm going to go end the session. Thank you all for attending. Like I said, there's going to be another info session on Wednesday, so feel free to hop on that. But it was, thank you for all your questions. And hopefully I'll see some of you guys in my office hours. So thanks so much for coming.